When you look at this picture, what do you see? A mother and her daughter, a family of ducks, plants by the shore of a river. Well, what I see when I look at this picture is water, because water is essential to all of them, to humans, to animals, and to plants. In fact, most of the Earth's surface is covered with water, over 70%. However, less than 3% of this water is available to us as fresh water, as most of the water is either found salty in oceans or trapped as ice in the poles. Now, I would like you to think of your favorite river or lake. How does it look like? Does it have beautiful vegetation? Is it a peaceful place? I invite you to try to locate this special place of yours on this map. And I will be using this map to tell you about the quality of surface water around the world. And by surface water, I mean rivers, lakes, or wetlands. Let's start by looking at the areas in green. These areas have shown excellent surface water quality, which means that you could go ahead and drink the water without the need to treat it previously. As you can see, there's very little green on the map. And to be fair, there are some areas for which we do not have enough information. These are the areas in light gray. Here, we don't know exactly what's going on. But we do know what's going on in the areas in yellow. These areas have shown some levels of biological contamination, which means that they can contain either bacteria or other microorganisms in the surface water. And the areas in orange have shown high levels of biological contamination. But biological contamination is not the only thing that could be harmful to humans and to the environment. Toxicity could also come from heavy metals or from human-made chemicals, such as pesticides or industrial chemicals. You look at the areas that are striped, these show some levels of toxicity. And the dotted areas show high levels of toxicity. Finally, the areas in purple have unusable surface water, according to the study shown here, for other reasons that are neither biological contamination nor toxicity. Well, as you can see, in most places around the world, you need to treat the water before you're able to drink it. How did we get here? How did humanity manage the water resources so poorly that there is so little green left on the map? To try to explain this, I'm going to walk you through history, starting with one ancient civilization, the Roman Empire. Romans already realized the importance of having clean, fresh water. And when it wasn't available to them nearby, they would build tilted channels and aqueducts to take the water from faraway mountains all the way to city centers. Romans also realized the importance of disposing dirty wastewater. So they built sewers to take water from households and public places all the way into rivers. So far, so good. Time passed, and we got to the Middle Ages. At this point, the infrastructures built by the Romans were only used in very few places. In fact, many people thought that bathing and hygiene were unhealthy. So we could also call these times the sanitary dark ages. And as time passed and the populations increased around the world, the chances were higher that someone would be living downstream of a city that was dumping wastewater into the river. In case there were diseases, bacteria or viruses could travel through the water and reach the populations downstream, which wasn't good. With time, people realized that, and in the Industrial Revolution, the first drinking water treatment plants were built, as well as the first regulations were implemented to dispose wastewater. And we got really good at removing things, such as bacteria, solids, oils, or metals. However, at the same time that we were building these water treatment plants, we were also introducing new chemicals to water, human-made chemicals, such as pharmaceuticals, personal care products, pesticides, or industrial chemicals. And the problem is that some of these human-made chemicals have a very stable molecular structure, which makes them very persistent, and the water treatment plants that we build are not able to remove them. We arrive where we're at now. Scientists are trying to find ways to remove these human-made chemicals from water so that they do not enter the water cycle. And today, I'm going to be talking to you about a particularly persistent pharmaceutical called diatrizoate. Maybe you or someone in your family has recently had a CT scan. In a CT scan, your body is scanned to look at your blood vessels, tissues, and organs. And in this process, pharmaceutical called diatrizoate is often given to the patients to enhance the contrast of the images, making it possible to detect things such as tumors. Therefore, diatrizoate is very helpful for medical diagnosis. However, as the patients leave the CT scan, eventually diatrizoate leaves their body through urine and enters the wastewater streams. And when wastewater from hospitals containing diatrizoate arrives to a wastewater treatment plant, it goes through different treatment steps. Typically, one of the last treatment steps is disinfection, which in many countries around the world is done with chlorine. Unfortunately, scientists realized that diatrizoate and chlorine react and form something that's carcinogenic. So instead of removing diatrizoate completely from water, we're producing something that's way worse. And let's say we don't want to use this chlorine. Well, in that case, diatrizoate would travel through the wastewater treatment plant without being removed and could reach rivers, lakes, and eventually it could also reach a drinking water treatment plant downstream, where at the latest there, we want the disinfection step because we do not want our drinking water to contain any bacteria or viruses. Again, in many countries around the world, this is done with chlorine, which just displaces the problem to later. Because chlorine can be quite problematic, some countries are thinking of banning it. And in that case, we have the problem that diatrizoate travels through the full water cycle and can reach us back through drinking water. So how do we solve this issue? This is where my research comes in. I use electric discharges to clean the water. Think of lightning over a lake or ocean. Now picture this very tiny inside a reactor. This is how my reactor works, and I'm going to walk you through it. Here you can see a picture of my reactor, which contains a small volume of water, about 80 milliliters, because it is laboratory scale. But this concept could be scaled up to treat larger water volumes. In a schematic, it will be easier to explain you how my reactor works. I start off by bubbling gas from the bottom of the reactor. And this gas is quite important, and I will get back to this in a few minutes. The next thing that I do is that I apply electric discharges over the water surface. You see, when you apply electric discharges over water, you can do two things. One, you can start chemical reactions that will degrade the contaminants and clean the water. And two, you can heat up the water. And we want to minimize energy losses. We don't want to heat up the water. In order to achieve this, what I do is that I put high voltage pulses that are high enough to start the chemical reactions, but then I stop the voltage pulses really fast, in less than 100 nanoseconds, before the water gets heated up too much. And I repeat this again and again over time. So high voltage starting the chemical reactions, and then stopping it very quickly, before the water gets heated. I do this 3,000 times in 1 second, which means that if I was doing a water treatment over the duration of this presentation, I would be putting in about 3 million pulses. Now let's see a picture of the electric discharge in real life. This is how it looks like. You may see that it is purple. The color of the electric discharge depends on the type of gas that's inside the reactor. And let's have a closer look at the chemical reactions happening in the reactor. In an electric field, electrons get accelerated. Electrons are the little balls, whereas the big red balls are atoms. Let's see what happens as the electrons get accelerated by the electric field. Let's stop here for a minute. As you saw, as the electrons travel down, they collide with atoms. And when they do so, an electron is kicked out from the atom. An atom is neutral, so if you remove an electron, which is a negative charge, what remains behind is positive. And this is what we call an ion. Therefore, by accelerating these electrons and having them collide with atoms, we're producing an ionized gas that we also refer to as plasma. Let's look at it again. Well, in a reactor, there's not only 3 atoms. There's a lot of atoms, a lot of electrons. It would look a little bit more like this. And not only are there atoms, electrons, and ions in an electric discharge, you're also producing other reactive species, such as radicals, excited molecules, or you can produce UV light. In a nutshell, this is a highly reactive mixture. And if this wasn't complex enough, remember that we're bubbling gas from the bottom of the reactor. This gas could be, for example, air, which would travel through the water and reach the electric discharge that we also call the plasma zone, and would react there. If we use another gas, for example, oxygen, the oxygen would also reach the plasma zone, And the chemical reactions happening when you have oxygen are different to the ones that would happen if you would have air. And this can be extremely useful. We will see this later in my results. Now, we have all these reactive species above the water surface. They eventually get to the water surface, diffuse into the water and react there, forming something that we call reactive oxygen-nitrogen species, also RONs, as scientists refer to them. So for the duration of this talk, I'm going to treat you like scientists, and we're going to call them RONs from now on. The purpose of using these plasma discharges and producing RONs is ultimately to clean water, to treat water. So what we produce is a plasma-activated water. And let's have a closer look at what happens inside this plasma-activated water. You could have a contaminant, such as diatrizoate, in the water, and as the RONs are traveling around, they eventually reach the contaminant. When they do so, they attack the chemical bonds, breaking the molecule into smaller and smaller pieces. I hope that now you have an idea of how we can use plasma to activate water and how this can break down persistent pharmaceuticals or chemicals such as diatrizoate. Now let's have a look at the actual results in the lab. I start off by using a dye. For the ones interested, it's called methylene blue. And the purpose of using a dye is that you can see changes very easily. The initial structure of the dye has a very deep blue color. And as the molecule is broken down into smaller and smaller pieces, the dye loses its color, which makes it very easy to optimize parameters inside the reactor with these changes. I started off by optimizing the voltage. Remember that we're putting in high voltage pulses to start the chemical reactions. So if we put in 5 kilovolts, it takes 70 minutes to remove the dye. If we increase the voltage to 7 kilovolts, it takes about 50 minutes to remove the dye. And finally, if we increase the voltage all the way to its maximum, 11 kilovolts, it takes only about 20 minutes to remove the dye. So we saw that with increasing voltage, we're able to remove the dye faster. And if we want to remove it the fastest, we would choose 11 kilovolts, the highest voltage. Well, remember, we're not only putting high voltage pulses, we're also repeating this over time. And in this case, we're putting 1,000 pulses per second. We can also change this. Let's fix the voltage to 7 kilovolts. And then if we do 1,000 pulses per second, it takes 50 minutes to remove the dye. Increasing the pulse frequency to 3,000 pulses per second, it takes half the time, 25 minutes. Increasing further to 5,000 pulses per second takes 12 minutes. And finally, if we increase it to 9,000 pulses per second, it takes only 8 minutes to remove the dye. So again, we can see with increasing pulse frequency, the dye is removed faster. However, in this case, my optimal parameter was not the highest, not 9,000 pulses per second. It was 3,000 pulses per second. And the reason is that I was limited by my power supply, which is homemade. It was built in my lab, and I was testing its limits. So when I was testing it at 5,000, 9,000 pulses per second, it was overheating, and I didn't want to break it. Therefore, I had this limitation. I had to stop at 3,000 pulses per second to be able to use the power supply long term. Now that we've optimized the voltage and the pulse frequency, let's put in this tricky contaminant, diatrizoate, in the reactor and see what happens. After 40 minutes, about 40% of diatrizoate is removed, which is already pretty good since diatrizoate is very hard to break down. So this is already a start. But I thought maybe we can improve this further. And as we cannot improve the voltage and pulse frequency further, what we could do is we could change the type of gas, which I mentioned earlier is quite important. Here, I was using an air plasma. It's the same type of plasma that I was using for the previous experiments that I showed with the dye. Well, by replacing this air plasma by an oxygen plasma, I was able to remove the dye almost completely after 40 minutes. Whereas with air, we removed less than half. So this is really great news. Now we can remove diatrizoate in a reasonable amount of time. And not only this, if we were using commercial power supplies, which are more powerful than the one that I have, we could remove it even faster. So now we've proven the concept that plasma can break down the molecule into smaller pieces. But now I'm interested in looking at these smaller pieces and seeing what happens to them, because I do not want any unintended consequences to happen, as we saw earlier on with chlorine. So what we did in my lab is that we took this solution of plasma-treated diatrizoate with all the small molecules that we had produced, these broken down pieces, and we did a standard toxicity test which works with bacteria. And the way it works is that you give the solution containing diatrizoate and the smaller pieces to bacteria. If they survive, it means that it's not toxic. And if the bacteria die, it means that it's toxic. And the good news is that the bacteria survived. And then we were able to prove that what we're producing is not toxic. Ultimately, my goal is to contribute to finding technologies that will be able to remove human-made chemicals so that they do not enter the water cycle. Not only diatrizoate could be removed by plasma, but also 100 other human-made chemicals. And I hope that water research around the world will lead to having more and greener areas on the map, so that soon, and for the generations to come, both humans and the environment can profit from clean water. Thank you.